Whenever I build a solar system model or draw a solar system diagram, and I want to use photons to describe planetary effects and gravitational or electromagnetic effects from a star onto planetary bodies, or the flow and direction of electromagnetism, I always have my 200 nm or 230 nm UV lamp going like crazy, and it produces quite a bit of heat. But what that does is it gives me a nice spectral wave. And so I want this UV lamp to represent the spectral cosmos around the solar system. So this is the daytime view. So the lighting changes quite a bit. It's Kepler 90. And there's a spread of lenses to see how electromagnetic fields or gravitational fields might possibly be moving through the Kepler system. So you just take a little light, and if we go like this, then we can start to see the bow shock wave represented by photons. And how it goes from lens to lens. You see it doesn't shine through K90B, but K90C is lit up. And if I just carefully manipulate the light, there, you can see how each planet directs a potential electromagnetic field or directs a potential gravitational field from the center of that solar system, which in this case is K90. And you can see how the light travels from lens to lens. And that bow shock wave that you see is hypothetical representation of the electromagnetic field. And the shadow bow shock wave can be representation of a hypothetical gravitational field. Now, as far as direct, people always want to talk about elements, but electrons and ionized charged particles travel in a direct route. And so let's just take this borosilicate rod. See? Now, by placing the borosilicate rod there, we have a nice example of how electrons will take a direct route and charged particles take a direct route. And then we can change the attitude of the borosilicate rod to represent a charged particle stream along with the light, which is the bow shock wave that you see there. You see? So there's Kepler 90F, but just do this. But right here in this area, you can start to see a hypothetical photon example of a magnetic or a gravitational wave. And then this is your direct stream. Oops, of course, is, sorry guys. And this, of course, is your direct stream of electrons or charged particles, and I'm using a borosilicate rod for that. Interesting how just from this lamp, though, the dispersion is quite fascinating. And it's completely inaccurate, of course. This is all hypothetical. But here's a charged particle stream going to K90D. And you can see how the lens behaves like a spherical planetary body. And look, even the charged particle stream takes on that same sort of bow shock wave that one might expect from a planet that is deflecting a charged particle stream. Let's see if I can just move that a little bit. There we go. And then here on Kepler 90F, you see that the charged particle stream is also creating a photonic example of a hypothetical electromagnetic stream passing by the spherical planet. And then you can actually pick up a little. Sorry about my sunblinds. You can actually pick up a little bit of the UV light passing through Kepler 90 right there. You see that blue-purple light? So that's why I use a borosilicate rod. I didn't get into it last night, but I use it to describe the direct pathway of electrons and charged particles. And so here is the sun. And here are the planets. And you can see that bow shock wave of how that could be representational of an electromagnetic field or a gravitational wave. And there's that one as well. And you can see how Kepler 90e has a array around K90H and K90G. And then there's a little K90F on its own over here. I hope you guys got a chance to look up the beautiful photograph taken 96 million miles from Earth by the Kepler satellite. It's a black and white, but it's a startling photograph. It makes our Earth look like a star. So, and there it is one more time. That's the Kepler system, just outside the Kuiper belt at 2,767 light years from Earth. Not too far away. I can't wait to go there. Maybe I should ask my friend. You guys have a great day.